So what I would like to do today is we'll talk about lime soda ash softening. So what the problem we're going to work on today is a lime soda ash softening problem. So as we've talked about before, groundwater often will have a high mineral content. You know that from living on campus. And lime and soda ash are the traditional way that we've used to remove calcium, magnesium minerals from a groundwater. So that requires reacting the calcium and the magnesium, typically with lime. So typically we add calcium oxide. Okay, so purchase the chemical as calcium oxide. We hydrate that with water to produce calcium hydroxide. So it's calcium hydroxide that we're actually adding to the water, but it's purchased as calcium oxide. And this is an exothermic reaction. So significant amount of heat is released. This is typically done in a well-ventilated, contained room to extract that heat. So we have a water. We're looking at achieving a final magnesium concentration of 40 milligrams per liter as calcium carbonate. So one of the first things to remember is that when we're looking at hardness and also alkalinity, the concentration units are typically milligrams per liter as calcium carbonate. We could use equivalents per liter. However, in the industry, the standard is to use milligrams per liter as calcium carbonate. So it's essentially a way of normalizing the concentrations to calcium carbonate. And that's because, as you'll see in these reactions, what we're actually precipitating is calcium carbonate. So why 40 milligrams per liter and why magnesium? The reason is that magnesium is actually more difficult and more costly to remove than calcium. And at concentrations greater than about 40 milligrams per liter, then the magnesium will precipitate at higher temperatures. So it precipitates in the hot water heaters and coats the heating elements. And that makes the heating process less efficient. It's going to cost you more in either gas or electricity in order to heat the water for use in the home. The other piece of information that I gave you here is that the pH of the water is 7.2. Why is that important? Why is the 7.2 important? Why do I give you a pH? For a closed system, and the analysis is similar for an open system. Those of you that have had 481 or are in 481 now, you will draw PC pH diagrams. So PC is the negative log of the concentration, and pH is the negative log of the H plus concentration. For the carbonate system, at pHs less than about 6.3, which is pKa1, as you can see here, carbonic acid predominates. Above pKa1, so this is pKa1, bicarbonate starts to predominate, and above the pKa2, which is about 10.3, then carbonate predominates. Okay. And alkalinity is equal to the concentration of bicarbonate plus 2 times the concentration of carbonate plus the concentration of OH minus minus concentration of H plus. So here our concentrations are in either millimolar or molar units. So if we look at here, in this pH range around 7.2, then the concentration of OH minus and the concentration of H plus, one, are small, and two, are essentially negligible. And if we're right in here, around pH 7, the concentration of bicarbonate is significantly greater than the concentration of carbonate, and this is also small. So one of the things to note is that for this water itself here, the concentration of alkalinity is approximately equal to the concentration of bicarbonate. And for those of you that are also in 480, we will talk about this afternoon because the first lab has to do with alkalinity. No, we've said that the concentration of bicarbonate is approximately equal to our alkalinity. So given the data that you have here, I'd like you to calculate the total hardness, the carbonate hardness, the non-carbonate hardness. I also want you to calculate what we would refer to as the carbonate hardness due to calcium, the non-carbonate hardness due to calcium, the carbonate hardness due to magnesium, and the non-carbonate hardness due to magnesium. Note, some of these may actually be 0, and that's common. Essentially gave you the answer to this, but I want you to think about it and talk about it in your group. Okay, 1, I didn't tell you whether you needed to reduce magnesium, but do you need to reduce magnesium? Think about why. And then why is magnesium used as a design parameter? So most of you, looks like, got that. It is the sum of the calcium and magnesium ions. Now, if I hadn't included sodium, so if I had the sodium here, do we include sodium in the concentration and the total hardness? No. Okay, we don't include sodium because remember your hardness are your polyvalent cations. So for instance, if we had a concentration of Fe3 plus or Fe2 plus, we would include that. Okay, so this is equal to the sum 167 plus 60 equals 227. The carbonate hardness then is that portion of the hardness associated with the alkalinity. So alkalinity is limiting. So this is equal to 197. And then the non-carbonate hardness is the difference. Now, I'm going to draw what we refer to as a bar graph here. And let's make this 200. Okay, so our alkalinity is 197. So this here is alkalinity. Okay, so we're plotting concentration, and we'll plot the anions and the cations. Now, the concentration of calcium is 167. So this is calcium. And then the concentration of magnesium is 60. So this here is that 227. This helps to then make some decisions about the carbonate hardness due to calcium. And we always put calcium first, then magnesium. It's in order of predominance, and calcium will almost always predominate over magnesium. So the carbonate hardness due to calcium is this yellow portion right here. So that is equal to the 167. The non-carbonate hardness due to calcium is equal to, so all of my calcium is consumed essentially as carbonate hardness due to, so the non-carbonate hardness due to calcium is equal to 0. The carbonate hardness due to magnesium is this portion, this green portion here. So that is equal to the 197 minus the 167, or 30 milligrams per liter. So the carbonate hardness due to magnesium is 30 milligrams per liter. And the non-carbonate hardness due to magnesium is what's left. And that is this blue portion right here. So that is we had 60 milligrams per liter of magnesium minus the 30, and that is 30 milligrams per liter. The next thing I asked you was, do you need to reduce the concentration of magnesium? And the answer is yes. The reason is the rule of thumb, and you'll see that there's a lot of rules of thumb that we will use in the semester. These are based on experience, that if the magnesium concentration is greater than 40, we want to remove magnesium. And we said that that was because at concentrations greater than 40, the magnesium tends to precipitate out on the heating elements in our hot water heaters. It would also precipitate on the heating elements in your dishwasher, and that causes problems with performance. And that's why it's used as a design parameter. Calcium is actually less costly to remove than magnesium. If we can achieve the desired hardness with only calcium removal, then we do so. The process limitations are based on a number of factors. One is the solubility. So we can write an expression, calcium carbonate dissolves to release calcium plus carbonate. And we can write an equilibrium expression, and that equals an equilibrium constant. We can do the same, and we precipitate the magnesium, not as magnesium carbonate, that's too soluble. We precipitate it as magnesium hydroxide. We can write a similar equilibrium expression
for magnesium hydroxide.
In this case, it is Mg2 plus times OH minus squared, and that equals the solubility product. Based on the solubility products, the minimum calcium hardness we can achieve is about 30 milligrams per liter, and about 10 milligrams per liter of hardness. That also includes that these reactions are not instantaneous. They take time, and there may not be complete time in the reaction basin in order to achieve equilibrium. And then, in addition, your basins are not going to have their ideal mixing. There may be short circuiting, so their concentration may be a little bit higher than that. So the next thing I would like you to do is to draw a schematic showing the split flow treatment and how to answer the question, how to determine the split ratio. So the first thing I asked you to do was to draw a schematic showing the typical flow. So typically we're dealing with well water. So any screening we do is typically done in the well. So if we have screening. So we have the softening process. Now, softening typically will include a rapid mix basin, followed by a reaction basin, which is actually very similar in design to a flocculation basin, followed by sedimentation. So that's just the typical process. So from that softening, we would then go into sedimentation. And following that, I'll explain just a second, but what we have is we have a bypass around here. So we're going to label that bypass X. And then the amount of flow that we treat is 1 minus X times Q. So we're treating a smaller flow than we would otherwise, which means we have a smaller reaction basin. We're adding less chemical. We have less sludge that we're producing, so therefore that reduces the cost of the sludge. So it's of significant benefit to the utility. Now, in processing or softening the water, the pH is going to range somewhere between about 10.5 and 11.3. We can't distribute water having that high of a pH. So we do one of two things. When we mix, it may be that the bypass is sufficient to reduce the pH when we mix the waters, or we may need recarbonation. So in recarbonation, what we're doing is we're adding CO2. That CO2 reacts in water to form carbonic acid, which then reduces the pH. Okay. And we may have, again, another sedimentation basin. To determine the split ratio, that this X, that bypass ratio, is equal to the final magnesium concentration that's desired minus the concentration coming from the first unit divided by the magnesium concentration in the raw water minus the magnesium concentration initial. So for this water that we're working with, our final is typically 40. We don't want to reduce the magnesium concentration any more than we have to, simply because of the amount of cost. The concentration coming from this unit, so concentration at this point right here, would be typically around 10 milligrams per liter. That's our process limitation. We start with 60. That was the initial concentration. That equals 10. So that is equal to 30 over 50. So we have about a 60% bypass. Okay. So that's our bypass ratio. In the interest of time, I'm not going to ask you to, we're not going to go back to breakout rooms. The final thing I would ask you'd be asked to do is to determine the stoichiometric amounts of soda ash and lime needed. So you've got these equations here. They're written for each of the reactions. We said we had 90 milligrams per liter as calcium carbonate. And that's the CO2 concentration. Now, actually, with that high of a concentration, you would typically not neutralize with lime. You would typically actually use air stripping to then remove the calcium, the CO2 gas, and then what was left you would actually neutralize. Okay, but for the sake of the problem, we'll assume we're neutralizing all of it with calcium hydroxide or lime. And remember, I said that CO2 reacts in water to form carbonic acid. So that means N is equal to 2, which is the same as calcium. So the amount that we need to remove is this 90 milligrams per liter as calcium carbonate. We're going to take 90 milligrams per liter as calcium carbonate. We're going to divide that by the molecular weight of calcium carbonate. And that is equal to 0.9. So this is milligrams per millimole. Sorry. So milligrams cancel, we have millimoles per liter. So we have 0.9 millimoles per liter. So we're going to write 0.9. The stoichiometric ratio is 1:1, so that is also 0.9. So we need 0.9 millimoles per liter of calcium hydroxide. We said that the carbonate hardness due to calcium was 167 milligrams per liter as calcium carbonate. We're going to do the same thing, divide that by 100 milligrams per millimole. And that is equal to 1.67 millimoles per liter. So that's 1.67. We need 1:1 ratio. We need 1.67. If you could stay on for a couple minutes, we can finish this. So carbonate hardness due to magnesium, we said this was equal to 30. So it's the same thing, 30 milligrams per liter as calcium carbonate. We'll do the same thing, divide by 100 milligrams per millimole. Okay, so this is 0.3. We have a 2:1 stoichiometry, so this is going to be 0.6. We have no non-carbonate hardness due to calcium, so we don't have to worry about that reaction. And then the non-carbonate hardness due to magnesium was 30. We'll divide that by 100 again. That is 0.3. And notice here, so this is 0.3. We're going to need both lime and soda ash. So the amount of lime that we need is equal to 0.9 plus 1.67 plus 0.6 plus 0.3. And that is equal to 3.47. And that's millimoles per liter. So that's how much lime we need. And the soda ash is equal to 0.3 millimoles per liter.
So then to calculate the mass per day, we would multiply this value by the molecular weight of calcium oxide
times the flow treated, but remember, that's going to be 1 minus X times Q.